So every time, every condition you can think of where you have an equilibrium, and instead of letting the market work, you distort the market, that's how we would say it as economists, and get a different outcome, then you will get to go along with that a dead weight loss. The way to think about a dead weight loss is you have a perfectly good chocolate bar, and you drop some of it on the floor and step on it. Yeah, that's a dead weight loss. It's value that went away. It's not value that somebody else got. Nobody got it. It just disappeared from the system. That's what I think of as a dead weight loss. It's not like the tax revenue. Tax revenue is not a dead weight loss. Tax revenue goes off and does something good, right? Or at least if you have a good government. If you have bad government, what does it do? Suppose you have bad government. What happens to your tax money? What? You spend it on? They spend it on themselves. What a wonderful idea. That happened in any countries you know? Okay, we won't name names. But yeah, but you know, when a minor civil servant happens to have like $300 million in cash in his closet in shoeboxes, that's a very large transfer. But it's not a dead weight loss, right? I mean, it's a strange redistribution of income, but it's not a dead weight loss. The dead weight loss is because the people he took it from, by taxing them somehow or other, instead of them doing what they should do, they did less of what they should do. That's where the dead weight loss comes from. So it's not, dead weight loss is not the money I stole. It's how I distorted your behavior and what that cost the system. I made you work too little by taxing you too much. Dead weight loss of taxation. Yeah? Yeah.
So willingness minus fixed cost.
Willingness minus variable cost is what we're looking at, right? But if we take fixed cost off there too, it makes no difference to the ranking of the things, because we're taking them off the best case, and then we're taking them off the other two cases as well. So, you know, if 7 is bigger than 4 and bigger than 5, then 7 minus fixed cost is still bigger than 7 and bigger than 5. That's all that's going on there.
Is it called profit or willingness minus?
Variable cost. No, the proper name would be quasi-grant. Yeah, but I don't need the name. It won't make me happy. It won't make me unhappy. It'd be perfectly fine with me to just say willingness minus variable costs. And if you're sloppy and said variable willingness minus costs, I'll assume you assume fixed costs were 0. Okay? So we don't have to go there. You may if you wish. It's just not required. Now let's go to the pollution case. You know, it's a little hard to get back and forth because of the way I drew these. Okay. So the pollution case you already know. It works by saying there is a cost to the system as a whole that the firms don't bear. I go for the simple case where the firm makes an output and it makes pollution, and the two are one-to-one. Every automobile I make causes 10 tons of pollution. There's no way to avoid that. So I've created a very simple case. You already know that's not true because you know that how the firm makes the product also has something to do with how much pollution there is. And I've just pushed that aside. I said there's only one way to make this product. Right? That's what I've assumed to get it on this particular graph. So now I have the firm's marginal cost, which I'll call MCF. And I'm going to add up MCF and the marginal cost of pollution to get the total marginal cost. And I would say total marginal cost because that's the least ambiguous way of saying it. If you look in the book, I will label one of these things social and the other one external. And I'm not wedded to it. Anything you want to defend will work. I'm going to go for the marginal cost firm, marginal cost of pollution, and I just wrote it as MC, and it's the sum of the two. Now, what will happen without regulation in this market is the supply curve will be the firm's marginal cost curve. It will intersect demand, and that will produce a quantity. That is the quantity the market will produce. And there it is. And this is the competitive solution, but remember, there's an externality. There's no reason to believe the competitive solution is the right solution once there's an externality. Why? Because the firm's not paying all of the costs. That's what's different. And look, I can see all of the different pieces. At Q, I don't know why I call it Q. Well, the competitive Q, I've got a blue triangle. I've got price, right, where the two lines intersect. I have a blue triangle under the price line and over the firm's marginal cost, and that is the firm's revenues minus the firm's variable costs. I have the consumer surplus, the ivory, right, under demand and above the price line. And we'll assume fixed cost is 0. That'll be convenient. So we call it profits. What happens now if instead of doing that, I do the right thing? The right thing is to make the firm pay all of the costs. To say the firm, polluter pays. The polluter pays principle. You, firm, create these costs for pollution, so why don't you just pay them? Maybe they pay them to government as a tax. Maybe they do something that makes the pollution go away. Maybe they give the money to the consumers to, as compensation. I don't know what they do, but they have to pay it. What happens if they pay it? If they pay it, then what do I got here? Here, wait a minute, I wanted to pay it. So I have marginal costs, all the marginal costs right here. So I have QS, the social answer, where the marginal cost curve, total marginal cost curve, intersects the demand curve. It's on the blue line. Quantity is less than it was for the case where it was just a firm and they didn't have to pay for anything. So quantity went down. But now you want to tell the story. First of all, which is the right answer? Should we arrange the world so that we are in the case where the firm doesn't account for its pollution or the case where it does? Which is the right thing to do as the social dictator. You get to be social dictator for a minute. What are you going to do? Yeah. So then which is the wrong one? The one where they don't. So if you're drawing this, the key thing to notice is that this is the right Q. You might even call it Q right. And this is the wrong Q. They make too much output because they do not account for their own pollution. Now, if you go from here, Q right, to here, Q wrong, you will get this red triangle, which we call dead weight loss. Yeah? What is it? It's the area under the marginal cost curve between the two quantities minus the area under the demand curve between the two quantities. Consumers are only willing to pay, from my fingers, the demand curve on down. Right? That's their total willingness to pay for this additional quantity. What is the variable cost of making the additional quantity? It is the red triangle plus the trapezoid underneath. When you subtract one from the other, the amount by which costs outstrip the benefits, which is willingness, is the red triangle. And that deadweight loss is the deadweight loss of pollution. That's why pollution is wrong. Or at least there's a money measure of how much the pollution is wrong. So we've now created two examples, haven't we? Created our standard tax example, in which quantity is too small, and you get a deadweight loss triangle on the left of Q right. We created a pollution example where quantity is too large. It's bigger than the quantity there should be, and we get a deadweight loss triangle on the right. The deadweight loss triangle always is bounded by the marginal cost curve and the demand curve. The trick in this diagram is to recognize what are the full costs. Once you realize that the full costs are MC as I've drawn it, the vertical addition of these two. By the way, if you took this distance and added it to this distance, you would get the top distance. That's how it's created. Right? So this curve plus the marginal cost marginal cost of pollution plus the marginal cost of the firm, when you add them, will give you that top marginal cost. So once you recognize the top marginal cost is the total cost of what they're doing, when you take account of pollution, then you know where the right answer is. It's where it intersects the demand curve, and you know how to calculate the loss from them making too much. It's the area under the total MC and above the demand. And so that's the story about what's wrong with pollution in a simple graph and how much value is lost. And that brings us to the general idea of deadweight loss, drawing diagrams and finding triangles that are losses. And the way you do it is first you've got to find the socially right output and find its willingness minus its costs. In the diagram before, is you had to realize that the total MC is the right social thing to do. Once you realize that, then you find its intersection with demand, you find its quantity, you find its willingness minus costs, and we'll call those willingness minus costs right, because it's the right way to do it. Then you can find any other output. One story we had was taxes. The other output, Q wrong, comes about because taxes make you make too little. Yeah? We have a different story. Q wrong came about because pollution, it made you get too much. Calculate out willingness minus costs for Q wrong, subtract one from the other, and that's the definition of deadweight loss. In terms of diagrams that we're going to draw, it's always going to be a triangle. It'll either be a triangle to the left or a triangle to the right. Yeah?
So the tax only pushes it back to Q right when there's no deadweight loss, right?
If you draw the example where the tax barely moves the quantity, there's no deadweight loss, right? None. So if you have a good that is demanded nearly perfectly inelastically, so the classic example would be something that poor people eat and everyone else eats, and if you try to change the quantity, the price will just explode on you. Yeah. So if you think of something like that, then taxing that has no deadweight loss. And therefore, we should tax goods that have low demand elasticities. And if you work out what goods those are, they tend to be goods that make up a larger fraction of the market basket of poor people relative to rich people. So it actually gives you as an answer, tax the poor. Yeah. You would not tax Mercedes because people would just buy smaller cars or different cars. Right now it causes deadweight loss. And Peter Diamond, Nobel laureate in economics, and Jim Merrilies, also Nobel laureate in economics, worked on optimal taxation. And what they did is they wrote out formulas that traded off essentially the deadweight loss of taxation for the income distribution effects, so that you wouldn't end up saying the optimal tax is to tax things which have little deadweight losses, and therefore it works out to tax the poor. Now let me just draw. I could draw it here. I can draw it on the screen. Let me try to draw on the screen what happens. So I want a demand curve, right, that's really steep. And I want just an ordinary supply curve. And I want a tax. Here's my tax. Right? And so now the difference between these two things is really small. Right? And the area under, there's my equilibrium. Now I want to go backwards, and my loss of, my deadweight loss is some little bit like that. Right? And you saw the diagram I had before. Make this thing. Right? Now if I have a similar amount of tax, here's my D minus T. Right? Now, I have a bigger deadweight loss. So as you take the demand curve and you rotate it up, then the triangle will get smaller and smaller and smaller, because the quantity difference gets smaller and smaller. Yeah. So you just reinvented classic finance, public finance. We have our deadweight loss of pollution, right, which we talked about. And we can go a little further. No, we can't. You could, but we won't. So you could also compare, if you wanted to, this, how much money the producers make in the two cases. And you'll find that they make less. That shouldn't be a surprise, but I don't think we're going to do that. Oh, we are. Okay. Same diagram, right, which you've seen before. And now I give the other case, the case in which I have a tax of T. The tax is carefully calibrated to bring me back to the same QS I found before. So tax will get you back to the social quantity. Yeah? And now we can look at where the money goes. Before regulation, we're out here, unregulated Q. We're looking at the area under the price. Price is found by marginal cost firm equals demand, and over marginal cost. And it's the two colored areas. And I have them both colored because when I change it, one of them will disappear, or largely disappear. And now what happens if I put on this tax? Well, if you put on the tax times quantity of tax is the green. That could go to the government if it were tax. Look what happens. All that's left of profits is what's left of is the blue, right? That's all that's left. The rest of it has all been squashed. So, of course, firms are not going to be happy to see that happen. That's not a surprise. Price went down for the firms. So, of course, they're going to make less money. But what could you do to keep them in the game? Well, you could bribe them, couldn't you? You have all this green tax money that just arrived. You want to get their cooperation because firms are people. We know that. Does anyone not know that firms are people? Firms are people, right? They're capable of spending money for free speech And their free speech could be, say, donating money to their favorite politician. Perhaps Koch Carbon has an owner who dedicates a lot of money on behalf of Koch Carbon to fighting regulations on carbon. Is that a strange thing to happen? No, that's not a strange thing to happen. That's what you expect to happen. So how would you buy them off in this world? Well, if you gave them a little bit more than what I've shaded in, then you've given them everything back. It has to be a little more because they've also lost this little red nose. So you have to sort of flip that in. You have to give them back that, and then the little red nose is like about this big. Okay? So if you gave them that amount of money, the first line is just continuing where this red was. If you looked at the red underneath, it could bleed through. You would see that there was a red triangle where I've shaded it red, and then I flipped this little nose on top of it. If you gave them that amount of money, then they're indifferent between the regulation and not the regulation. And there's still extra money to take home, and pollution goes down. So that would be a way to do business. In fact, what we tend to do is we tended to do quantity regulation, in which case, who gets the green thing? The firms get it, right? The quantity regulation. Yeah. You may not make more than QS, the price will be, no, actually, you have to make QS, the price would be way up here. Yes, that's right. And so they would get the green thing. And that overcompensates in the way I've drawn the diagram. So in some sense, we're probably overcompensating them. The cap and trade programs we have big fights over basically what to do with money. So if you take the allowances and you auction them, then the money appears to the government. If you take the allowances and you give them to the firms, then the money appears to the firms. And the California program takes some of the money and gives it each way. And the idea is to give the firms enough money so that they're not too angry at you, while at the same time not giving them all the extra money. That's the concept. Yep. And here we formally do the taxes. Here I've taken marginal cost. I've added the tax to marginal cost. Right? That's one way of solving the problem. The other is to subtract it from the inverse demand curve. I found the equilibrium, QE. I found the tax equilibrium, QT, in the usual fashion. And now I can look at going from QE to QT, what happens, how much costs are avoided, the light blue area, the area under marginal cost. There's marginal cost. How much willingness to pay is given up, the area under the demand curve between QE and QT, the two areas together. Which one's bigger? Well, the two areas together are bigger than the one. By how much? By the dark blue triangle. So the dark blue triangle is the deadweight loss of taxation. It's the amount by which willingness minus costs goes down when quantity goes from the correct quantity, which here is the market quantity, to the taxation quantity. And that's the deadweight loss of taxes diagram. Okay, yes, go back. Because I can't draw. Yes, that's the only reason why. If you're drawing it, draw them parallel. Absolutely. Should be parallel. Should be parallel. You're correct. It should be parallel. All right. What time do we have? So we'll keep that. And no, we have some things to look at. Where is the thing I want to look at? Oh, there we go. So this is a paper by, this is a paper that I'm going to have to get up again. This is a paper by Skip Leitner, who's an energy expert. And the key thing in it is one diagram. Well, one chart and one diagram. So if you were an engineer and you're doing energy efficiency, you make up a large list of technologies. Here, he has a list of emerging energy efficient industrial technologies. I don't know what they are. One of the second one is improved recycling technologies. And he does all this work, and he claims that it'll save 2.2 teraBTUs, and it would take 4.5 years for this technology to pay back a person who implemented it. So if you're a firm and you do this technology, it's going to save you money, but it'll take 4.5 years for the money you save to pay you back for your investment. Yeah? And he makes up a long list of these things. Then he takes this long list, and he puts it out as a diagram. And this diagram has come to be known as a conservation supply curve. And you'll see them all over the place. What it says is, if you wanted a cumulative energy savings of 1,000 teraBTUs, then you could do it at a cost of near zero. And it's 3 lines differ in how they discount the future, and I don't care about that for the moment. Just pick whichever line you like. I'd say pick the blue line because it's easiest to see. Right? And actually what he finds is that at near zero cost, you can save up to 2,000 teraBTUs. There's quite a lot of energy. And then after that, it rises slowly. And he thinks that the 2015 fuel price, which is coming soon, will be $54 per million BTU. I don't know what it'll really be, but that's his assumption. This is a little bit old. And so he would say,